Okay. So let's kind of review what we did last time before the test from section 6.1. Yeah. Oh, glasses would be amazing. There they are. How did I do anything before I get into it? How did I do anything before I use glasses? Okay. So the idea of eigenvalues is so deceptively simple. In fact, we have done eigenvalues and eigenvectors before this. When I have a projection matrix, what is its job? Projection matrix. What is its job? What is it built from? Let me say it like that. What do I build a projection matrix from? Subspace. Yes? You with me? I don't have to be given any vector. I can just make the projection matrix and have it sitting there ready for when a vector comes. And what's it do when a vector comes? Did you say eat it and shit it out? You said shoot it out? Shoot it out. Okay, I thought you said shit it. Would be hilarious. Alright. You guys all come with me? Remember the potato? Potato. Okay. You get the projection matrix set for a subspace. Some vector that's not entirely in the subspace might come along, and it just flattens it into the subspace. Yes? So in data analysis, that's called compressing, or even with, I talked a little bit about algorithms that try to compress the bit rate and so forth so you can actually transmit stuff. So it's all about compressing and then leaving enough so you can build it back up. All right. If I have a vector that's already in my subspace, what will the projection matrix do to it? Nothing. So if I have a vector, become a thing, B, and let's just make it what we normally are used to, in the column space of A, and I've built a projection matrix that represents the column space of A, PB would equal B. So what's lambda? 1. So, let me really, just to kind of get back in the flow, we'll get into the nuts and bolts of how to calculate eigenvalues, but I want to point out a situation where we already have it. So an eigenvalue goes with an eigenvector. Lambda is 1, meaning operating on a vector, specific vector, that lives somewhere with this matrix P is essentially the same thing as multiplying that vector by 1. So the idea of eigenvalues, eigenvectors is if I operate with a certain matrix on a certain vector, if the result is a scalar multiple of that vector, that is kind of like what eigenvalues and eigenvectors are all about. So this is one example of something we just saw in the wild. So lambda equals 1 goes with B vectors that are an element of the column space, yes? Now, in the same situation, what if, just to give a different letter, what if D is not in the column space of A? In fact, even better, what if, more powerfully, D is orthogonal to the column space of A? What is PD? 0. Right? Because now it's got no component that I can push. When I compress this, I compress it straight down and it becomes a 0 vector. Whoops. So if I have something that's got a little bit, when I compress it, I get this little tiny bit that's in my column space, yes? But if it's perfectly perpendicular, when I push it down into my space, I'm like, oh shit, it's all good. I just got this little 0 vector. Yes? Are you guys kind of with me? Okay. So in this case, lambda equals 0 goes for vectors that are orthogonal to. So this is an eigenvalue that goes along with its eigenvector. So this is the key. And when I operate with a matrix on a specific vector that lives in a specific place, the result would be a multiple of that vector. So eigenvalues go together with eigenvectors. It doesn't mean that if I get an eigenvalue of 2 for matrix A, then matrix A equals 2 somehow. Yes?
Didn't eigenvalues have to be non-zero, or is that just...
Oh no, they can totally be 0. Yeah. They can be negative, they can be 0, they can be complex. Yay, Jeff. Are you gonna have to work with those?
Yes.
Yes.
So the eigenvector, and that's going to be B?
Yes, and specifically, the eigenvector that goes with an eigenvalue of 0 lives in the orthogonal space, the column space. Is that cool? So it's perpendicular to the error vector. Yeah. I'm sorry, parallel to the error. You guys, that's a wonderful example of a situation where we didn't even realize that's what was happening. So this is just an example of, I'm not suddenly going into something that's so weird and it just happens on the edges. This kind of shit happens all the frickin' time. So given a matrix, my question then becomes, does this matrix have eigenvalues, and what are they? And what are the vectors that it acts like that? So I'm like, the matrix A sometimes acts like 2 times. When? That would be the next step. So I figure out what are the eigenvalues, and then what vectors makes the matrix act like that. Sorry, you guys are looking like, yeah, okay. So just to remind you guys, this is beautifully simple math in the middle of all this weird ass concept. Did we do it here? Let me do a fresh example. Blah 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 yakety schmackety. Where did I end up? Oh, here we go. Here, let's do something here based on that last question I just got. I love it. Let's do this vector, Jeff. This matrix. So I'm not going to rederive the idea. If you weren't here that day, you can watch the video. But basically, I want this to be, I guess I am going to rederive the idea. Jeff, stop it. Don't do that. I want this to be true. Lambda is just the symbol we chose to use, just to make it even less accessible to students. Yes, so we should do something Greek here. Lambda represents a scalar. Lambda is the number that multiplies a vector, and the matrix A acts like that sometimes. Another way to look at it is A becomes a stretch. It stretches the vector in certain situations. Okay. This leads to, just to do this very quickly, this leads to this, which leads to this. It should be this, Jeff, because it doesn't make sense to have a matrix minus a scalar. Yes? Somebody write that better. Bless you. Can somebody write, in this situation, what does lambda I look like?
Just to eigenvalue.
No, what does lambda I look like, just by itself?
Lambda 0, 0.
Yeah. So lambda I looks like lambda 0, 0, lambda. Oh my God, my lambdas are all over the place. So then, can you guys take a second and write A minus lambda I, write that below this. What does A minus lambda I look like? A minus lambda I.
Question.
Yeah.
Earlier you mentioned potentially talk about would that be linear transformation CDP?
No, that one I'm gonna keep. I'm not sure yet what I'm gonna do. So that's why I said I'll let you know next time.
I've seen other textbooks that put linear transformations like in the middle.
I know. Yeah. A lot of what we're doing later in the class is normally earlier in the linear algebra class. I like some of the idea behind Strang's ordering, but I also don't like some of it. All right, so what does this look like? Yeah, 1 minus lambda 2, 4, 8 minus lambda. So just the stuff in the diagonal are affected. Can you guys take a minute and just figure out what the determinant of that is? Now, real quick, just to show you why I'm doing that. What is the trivial, what is the uninteresting, boring answer to this? What if my vector x is 0? Then I don't care what matrix I'm multiplying it by. It's going to look like lambda 0 for everything in the universe, and that's dumb. You guys kind of with me? So I'm not even going to let x be 0. So what is the only way that this could have a non-trivial solution? You could do this. When will ax equals 0 have a non-trivial solution? When will ax equal 0 have a trivial solution? When will ax equal 0 only have 0 as the answer? If a is sure, which means it's invertible, yes? Because then you just do a inverse to both sides, so you get x equals a inverse 0, which is 0, yes?
The determinant is not 0.
So I want to force the determinant of this dumb thing to be 0.
To be 0.
Yes. So you were answering, I thought you were answering my question earlier. So if the determinant of this matrix is not 0, then the only answer is x is 0, and we all just agreed that's hyper boring and not useful. So let's not let that be 0, which means the determinant of this has to be 0. That's the only way it could have non-trivial solutions. Yes? I want that to make nothing but sense. And you guys are looking like, me too, Jeff. Could you try again? If the determinant of that matrix is 0, that leaves the door open for the null space to have actual entries in it besides 0. So then I get the eigenvectors that go with eigenvalues. Can you take a minute and just figure out what the determinant of a minus lambda I is? So let's see, if you do this times this, you get lambda squared minus 9 lambda plus 8, yes? And then you minus, so that was this times this. Minus 8. And I want to make that, I want to force the determinant to be, we've already forgotten, damn it, 0, yes. 8's go away. How do I solve this equation? Factor out a lambda. And this was the earlier question somebody had where you thought lambda couldn't be 0, but lambda totally can be. So lambda is 0 is one eigenvalue, lambda is 9 is another one. Now, real quick, did anyone notice something about this matrix from the beginning? There's something about this matrix. There's something about matrix. The columns are dependent, which means this matrix, don't mean anything you know. The columns are dependent, which means the determinant of A itself would be 0, which means not invertible, right? Which means the null space for the matrix itself, does it have non-zero vectors in it? You with me? Yes, the null space has to have dimension at least 1. It's got to have dimension 1, yes? You guys, is everybody with me? I want this to make sense. Everything in the null space, if I take a vector from the null space, I'm going to call it x. You with me? What would ax be? 0. That's the idea of anything in the null space, right? Are you guys at all with me? Every time we've ever discovered a null space with a dimension more than 0, we have discovered eigenvalue 0, eigenvectors are the vectors in the null space. We just didn't say it like that. Why? Because if I apply a to any vector in the null space, it acts like I'm multiplying by 0, correct? Because what is a times x if x is in the null space? 0. So therefore a acts as if it's just 0, yes? The more interesting part of this point, now that's interesting by itself because it's connecting to stuff we've done already. So here, once you get your 2 eigenvalues, you're about halfway through. Now you plug them back in, yes. So what does this matrix become in the event that lambda equals 0? Yeah, then you just get 1, 2, 4, 8. How do you get its null space? I mean, can you see, do you have to row reduce, or you already know this is going to be 0, 0, yes? Yeah. So then what's got to be true about x1 and x2? Is that cool? I mean, is everybody with me? This is old shit now, yes? And so therefore, x1 must be negative 2x2, so then if x2 is 1, x1 would be negative 2, yes? And officially this is any multiple of it, but I call this the eigenvalue. I'm sorry, the eigenvector that goes with this eigenvalue. What did we used to call this, or what is it still? This is the basis for the null space. Yeah? So again, this is old shit. We weren't there yet to call it Eigen-stuff, which is the way I reference eigenvalues and eigenvectors, just Eigen-stuff. How you guys feeling? So this relates to null space work we have done a lot of. Every time you've ever done null space and you found some vectors, you found an eigenvector with an eigenvalue. Can you guys do everything we just did, but this time do it for lambda equal 9? Do everything we just did, but now make lambda equal 9. So go back to your a minus lambda I, make lambda equal 9. Ooh. Everybody else got their test back, right? Test. Okay. Oh. So you get -8 to 4 -1. So again, this leads to a. Now, what should make sense is, if you do happen to get eigen values, you'll start to notice a pattern about the resultant matrix. Because I have to get it equal to 0. That's the whole idea. So these have to be dependent. That's what kind of started this whole thing off. So again, I can do it whatever way you like to do it. If I row reduce this, this would become 0, 0, yes. And this would become, I don't know, whichever way you want to do this. How did I do it? Oh, I did it like that. So this, I can make this 4 -1. Is that cool? Is everybody really cool that just happened? I don't have to show all the freaking steps. This is easy. They're dependent, kill one, reduce the other one. So then what must be true, or can somebody just write the vector that goes with that? Yeah, 1, 4, kick ass. Yeah, 1, 4 would make it 0, yes? So when now, can everybody please take A and multiply that by 1, 4? It's really sad. Really sad that I didn't leave enough time for the end here, and I'm sorry. I'm gonna try not to cram too much stuff in, because that's just insane. I'm gonna try to kind of tease little things that you can look into more. And we're about to do one freaking nifty thing. This is gonna be kind of silly. You should all know exactly what's gonna happen. But if you actually work it out, what do you get? And why does that make sense?
That's a multiple of 1, 4.
Well, no. It's a multiple of 9, right? Lambda, if I operate on 1, 4, the result should be 9 times that. Yes? Are you guys with me? If I operate on any vector that lies in the direction of 1, 4, I should get 9 times the beginning. That's what I figured out. When I have a vector that lives in the space spanned by this, the matrix A acts like multiply by 9. A does not equal 9. It acts as if it's just multiply by 9. All right, guys, how's that? So then a really good question would be, okay, Jeff, what does it do to 1, 3? Mr. Math Man. We'll try it. I'm going to pretend like somebody actually asked me. Do you guys understand? This is just playing around with shit, but this is actually not just playing around. This is a very integral idea. Can you guys please, some of you guys are just staring at me, some of you staring at your desk. Can you go ahead and take the matrix A and multiply by 1, 3? Is 1, 3 very far from 1, 4? No. But we don't really know what we're going to get because we don't have any definition of what's supposed to happen. What do you guys get? What do you get? 728. I like it. What am I looking? Oh, that's for later. I looked at the wrong place. There you are. Now, what is interesting about 728?
It's also an eigen.
Say again?
It's an eigen vector.
No. Okay. I want you to realize this matrix has only two eigenvectors, 0 and 9. Are you guys with me? I could take a matrix anywhere in the universe and multiply it by a vector and get 3 times that vector. Does that mean that 3 is an eigenvector of that matrix? No. It's just a coincidence. I'd have to prove it, in which case every vector in that direction would become triple once I operate on it. Are you guys at all with me? I could operate on a vector, which is some random matrix, and the answer comes out to be 3 times the original vector. Does that make sense by itself? Does that mean 3 is an eigenvector of the? No, it doesn't have to be. It would only be an eigenvalue if every vector in that direction had that happen. Yes? So look at this guy. This is weird. So Zach, I understand. What did this end up doing? It didn't do anything to 1, 3 necessarily, right? It did, but it kind of like, what does it look like it actually did? It took what vector, which is important. What vector is important to this? 1, 4. And you can see kind of why. It's built on 1, 4. And this vector, sure enough, is 4 times 4. I love you, Jeff. 7 times 1, 4. So it didn't do 7 times 1, 3. It didn't do 9 times 1, 3 for damn sure, yes? It could do whatever the hell it wants to, but it's weird that it came back to along that direction of the eigenvector. So here's the idea. If I take, okay, how do you guys feel about just eigenvalue, eigenvector, the work involved? Do you guys realize it's not that deep? Now obviously a 3 by 3 matrix, the factoring is going to be a little more interesting. Okay. So then we have to start talking about, is there a better way? Could I row reduce a little bit and then find the eigenvalues? We'll have to talk about it. The 2 eigenvalues for this were 0 and 9. Yes? When you operate with the matrix on something, the result you get is a combination of effects from both. The fact that one of them is 0 means it ends up not contributing at all. So the really cool thing, if I have one of my eigenvalues is 0, and I have let me see if you guys are cool with this. I have the eigenvector, and I have a vector not lying along it, yes? If I do one application of the matrix, it will make the result lie in that direction. You guys with me? So that is not a coincidence. If one of my eigenvalues is 0, one application of that matrix on any vector will cause that to line up with the eigenvector. Because lambda equals 0. If neither one of the eigenvalues, if none of the eigenvalues was 0, then when I apply the matrix once, it'll bring it closer. When I apply it again, it'll bring it closer. When I apply it again, it'll bring it closer. So the limit would be it would line up perfectly, because whichever lambda is biggest, the other lambda's influence gets smaller over time. So it's kind of trippy. Now, can you guys take this vector and apply A to it again? It's kind of silly. You guys should know what's going to happen. I think this book, I can't remember. I almost don't care what Strang does. Let me see. I don't remember. What does he do? He doesn't do shit. That makes sense. Okay, that's fine. We'll be okay. So, what are you guys getting? What is it?
63 times 4, but 252.
So you're getting 63 and do it again? 252, thank you. Okay. And if you divide that by 63, you get 1/4. 252 divided by 63 is 4, and 63 divided by 63 is 1. So did it now multiply by 9? Did it take my vector to start with and multiply by 9? Yes, it did, didn't it? Why did it do what it kind of like wants to do? Because I fed it 1, 4. Yes? I can rewrite this as 7 times 1, 2, 4, 8 times 1, 4. I don't have to do shit because I know this when it attacks. Holy shit, Jeff. When this attacks 1, 4, it just makes it become 9 times as big. And then I can just multiply that shit by 7, and I get back to here. Is that cool? So what's really cool, if one of my eigenvalues is 0, this trips me out so much. It just snaps. If I apply it once, it snaps it onto the direction of the eigenvector. The multiplier, like our multiplier was 7. Why isn't it 9? Because I didn't feed it the right vector. But it did immediately snap it to be in the direction it wants it to be in. Yes? We just don't have the time, but can you see how that type of action is remarkably important when you have certain directions that are kind of important in what you're applying? I want them to snap to this direction. Maybe. So we're just barely getting into this, and there's a lot of cool shit you could do with this stuff. Okay. I kind of want you guys to get used to the nuts and bolts of this at the same time. I'm talking about some higher level weird shit. By the way, if I attack 1, 1 with this, I get 3, 12. Again, it's a multiple of 1, 4, right? Okay. So let's look at this here. Yeah. Why is this one? I'm going to make a little shortcut out of this after we talk about it a little bit. What is really nice about that matrix? Is lower triangular. You could just say triangular. Ooh, cool. Which means any determinants I've defined are going to be easier. Yes. In fact, the determinant of this matrix itself is what? 12. How do I find the eigenvalues? What do I set up? A minus lambda I. What will that be in this case? And I'm going to do the determinant just to get all the work here at one time. 3 minus lambda. 0, 0. 1. 4 minus lambda. 0. That's right. And why is that determinant easy as shit? Because what you just told me, right? So can you guys see a shortcut? This is too nice to believe. I mean, is everybody cool with this? That is what the determinant is, yes? Because I'm going to choose the freaking, you don't have to choose the top row, but if you don't choose the top row, you're weird as shit. Or the last column, I'll take that too. Right? The further you get away from those two things, you get a little bit weirder. But it doesn't matter which row or column you pick, because of those zeros and where they are, the determinant ends up being just the product of the diagonal, like you said for the original one in the first place. Did I even have to do that shit then? What are the eigenvalues? 3, 4, 1. 3, 4, 1. And you know, hopefully you guys all see, well, of course, Jeff, holy shit. So if I have a lower triangular or upper triangular matrix, I can get the eigenvalues by just looking at the pivots, right? Looking at the diagonal. You guys coming with me? Okay. Can you guys go ahead and figure out the, do I want to do that here? Sure. Let's look at one of these. Can you guys figure out the eigenvectors for lambda equals 3?
0, 0, 0, 1, 0, -2, 1, -2.
-2, 3, 1. So if lambda equals 3, let's see, you'll get 0, 0, 0, 1, 1, 0, -2, 3, -2. I like it. Now this is our first direct 3 by 3 matrix. I just need to get the null space of this, yes? That's the whole idea. A minus lambda x equals 0. A minus lambda I times x equals 0. So I just need the null space of this. Can't you row reduce to kind of help yourself out a little bit? right? Kind of get leading ones, get it in that format. That's an easier way to get the null space. Do you have to do that? No. So if I kind of row reduce a little bit, 1, 1, 0, I'll get, if I double that, I get 0, 5, -2. And then if I multiply, how do I want to do this? Oh yeah, okay. How do I want to do this? Oh yeah. So if I take, oh, I just want to do that. Duh, me, I'm smart. So if I do 0, 0, 0, 1, 1, 1, 0, 1, -2/5, and then I could kill that 1 there. I get 0, 0, 0. 1, 0. 1 minus 0 is 1. 1 minus 1 is 1. 1 minus 2/5 is 3/5. 0, 1, -2/5. Okay. Woof.
There's supposed to be 0 in the second row, am I right?
Maybe. Let's see. Oh yeah, why did I put a 1 there? Become a 0. So this will be 1 minus 0. 1 minus 1 is 0. And then 0 minus 2/5 is positive 2/5. Okay. And then what's the null space basis? How would you get that? So you could, if you wanted to, you got x1 plus 2/5 x3 equals 0, and x2 plus, I'm sorry, minus 2/5 x3 is 0. So obviously, you already knew that x3 was going to be your free variable. Yes, you're going to end up with x1 is -2/5 t, for example. x2 is 2/5 t, and x3 is t. So you end up with, if I multiply by 5 just to make it better, I'm going to get -2, 2, 5. Okay, that looks much better. I probably could have done that a little better, but it's just between my mind quickly. So what does that vector do again? Or what does that vector cause to happen? Or what happens to that vector? If I operate on it with A, it becomes 3 times as big. Yes, I like it. What happens if I operate it with A twice? It was 9 times as big. Yeah. So the whole idea of eigenvalues, and we're going to factor a matrix in a certain way, so that if I had to do A to the 48th power, can you imagine doing A to the 48th power for this? And this is lower triangular. This is pretty good. Do you understand what I'm asking? Do A times A, get a matrix. Do that again until you get A to the 48th power. Do you understand what I'm saying? Do you want to do that? Good. I really want to do it. So we're going to develop a shortcut to get powers of a matrix based on a factorization I could do using eigenvalues. You can kind of see this is a hint at that. A squared is just multiply that vector by 9. A cubed being multiplied by 27. Yes? Okay, maybe. Go away. And I didn't do all of them, but you could take each eigenvalue and get their eigenvector. We could have similar conversations. Okay. What about, let me see. No, I don't want to do that too early. What about, I don't want to do that one. Here, okay, beautiful. Yeah, that's perfect. Okay, perfect. Wait a minute. Yeah, I want to do that. Okay. So what happens, what kind of matrix is this? What's going on here? Tell me everything you know about that guy. Symmetric.
Yeah.
Is it invertible? Yes.
Is this 6-1 stuff?
Yes. I know, it's all going to blend together. Sorry, Zach. Okay. Just to do this very quickly, I'm just going to hop straight to putting the determinant together. Is that cool? That's my a minus lambda I. I want to force the determinant to be 0. So I get lambda squared minus 2 lambda plus 1 minus 16. Is that cool? You guys cool? You guys all right? Okay. So So then, do that real quick. Get the two lambdas. Okay, sorry. So you get, what do you get? You get lambda squared minus 2 lambda minus 15 is 0. So you get lambda minus 5, lambda plus 3. So you get lambda is 5 and negative 3. Is that cool? Very quickly, what is the determinant of this matrix? Negative 15. And what is the product of the eigenvalues? Okay, that's going to come up in a bit. If you look back at every problem we've done so far, you can verify that's true. For the lower triangular, it's obviously true. And that kind of tells you why it might be true in general. Does it really help you find them? No. But it is just a nifty little thing. So if I plug these back in, just to kind of do this a little quickly, I'll get negative 4, 4, 4, negative 4. Does anyone know what the eigenvector that goes with that would be? 1, 1, kick ass. And if I do the other one, this would be lambda equal to 5, sorry. So lambda equal to negative 3 would give me, where'd I go? There I am. 4, 4, 4, 4. And so what would this lead to? Yeah, either 1, negative 1 or negative 1, 1, yes. It doesn't matter because they're both like multiples of each other, yes. What kind of vectors are those two eigenvectors? How do they relate to each other? Do they get along? Would they survive a road trip together? They're orthogonal, yes. So in general, let me see if I want to prove this. Why not? It's a quick little thing. If I have real symmetric matrix, if I have a real symmetric matrix, like one you're not imagining, it's actually there, and it's symmetric. Real just meaning is real valued. Then I'm always going to get eigenvectors will always be orthogonal to each other. Orthogonal. Okay. I got a little tired at the end of that word there, sorry. Yeah, so if I know it's real symmetric, what do I automatically know about it? I know that A transpose is A, correct? Yes, yes, yes? Okay. And let's say that AX equals lambda 1x and y equals lambda 2y. So x is the eigenvector with lambda 1 and y is the eigenvector with lambda 2. There you go, Jeff. You guys kind of with me? And I'm going to assume that lambda 1 is not equal to lambda 2. So here we do a little bit of weirdness. And this is actually something that's going to come up later. If I start with, ooh, wait a minute. Did I write that wrong? Let me see. Oh, okay. Yeah. Oh, okay. Okay, here we go. This is going to be a little weird. I kind of started at a weird place, but let me see. The step before that was this, Jeff. Yes, okay. I'm going to analyze this for a second for some weird reason. Do you see how I have an eigenvector that doesn't go with its eigenvalue? Mm-hmm. Okay, I love you guys. Y'all look appropriately freaked out. Now, is this okay? That's a transpose property. What is this? It's AX. And then what's AX transpose? X transpose, A transpose. And what's A transpose? A. And what's AY? Yeah, Y2Y, yes? I'm sorry, lambda 2Y. So X transpose lambda 1Y equals X transpose lambda 2Y. So therefore, you left, I love you, Jeff. You leave stuff out. I love it. Let me write this down and think about it for a second. Okay. Lambda 1 X transpose Y equals lambda 2 X trans, oh, okay, this is just a number, so I can just put it out front. I'm so silly. Is that cool? Y2, lambda 2 and lambda 1 are just numbers, so I can just put them out front. Yes? So, real quick. Lambda 1 and lambda 2 are not equal to each other. So, what is the only way that this statement could be true then if lambda 1 does not equal lambda 2? What must be true about X transpose Y? It must be 0. And what does that mean about the vectors X and Y? They're orthogonal. Oh my God, Jeff. That was longer than I thought it would be. Sorry. Past Jeff decided to not write every step down. Just keep some of it in his head. All right, that was just a quick, if I have a real symmetric matrix, any eigenvectors you end up with will be orthogonal to each other. Just kind of a good thing to know. Okay. Here's another little tiny thing. I'm not even going to do an example of this. But if I have a matrix A and the columns add to 1, then lambda equals 1 will be one eigenvalue. Might have another one. Who knows? Yes?
What do you mean the columns add to?
Oh, all right. So let me give you an example. It's exactly not what you would think. It's just that, right? That's what I mean. 2 plus negative 1 is 1. Negative 2 plus 3 is 1. The columns add, let me say it like this. All the elements of each column add up to be 1. Is that better?
Okay. Isn't that 0 too?
Yeah, that's.
2 minus 1 is?
Other row.
2 minus 1. So the numbers in the columns. That's what I'm trying to say. I'm sorry. The numbers in each column will add up to be 1. Okay. English is my second language. Math is my third language. First language is Jeff, which is, who knows what that is. Okay. So let's talk about an example of something that has imaginary eigenvalues. Can somebody, what is up with this matrix, for example? Is it symmetric?
No.
Hell no. And this is I can't even remember if I even said this phrase, but this is what's called skew symmetric. The transpose is the negative of the original. So whenever you have something that is skew symmetric, you will end up with complex eigenvalues. Can you guys kind of go through the process of trying to set it up? Try to get the eigenvalues. Say again? Negative.
Well, like for like when you A minus seven.
Yeah, your BD is going to be negative, so you end up with the plus, yeah, which makes a problem. Yeah, I got you. Oh my God. There's so much stuff here. Okay. Oh yeah, okay. I'll do that a little bit. I'll do that, yes. And that'll be it for that. Okay. Oh my God. So if I set up my A minus lambda I determinant, it'll be negative lambda 2, negative lambda, and that would be lambda squared plus 4, yes? You guys are in 284. What are the answers to that?
Plus or minus 2.
Plus or minus 2i, I like it. Is that cool? So let's see what happens if I try to get the eigenvectors.
Wouldn't you not be able to do it because you have to minus the 4 to the other side. Or
Oh yeah, totally. That's what we did. What's the square root of negative 1?
square, wouldn't there be an error?
All right. Side note, because this is going to come up very, very soon. You're good, Zach.
Yeah.
You have paper, Jeff. It's right there. Very quickly. Don't even write this down. What do I get when I multiply 1 by negative 1?
-1.
Negative 1. That is a rotation of 180 degrees. We don't define it like that because we don't want to trip the hell out of these little people. Rotation? No, 1 times negative 1 is negative 1. Okay. Okay. So I often talk about when I taught math 88, when we actually offered that here, I would say multiply by negative 1 is like turning. And then if I multiply by negative 1, I turn again. And the honest fact is that is exactly the mathematical truth. This axis, so real quick, 1 times negative 1 is negative 1. Negative 1 times negative 1. I rotate again by half a rotation, so of course I end up back at 1. Woo! So what happens if I do a quarter of a rotation? So I don't do 1 times a full negative 1, I do 1 times half of a negative 1, multiplicatively. And another way to say half a negative 1 multiplicatively, well that's one way to say it, is the square root of negative 1. Yes? How many of you guys knew that complex numbers live on these? So if you draw a parabola and you pretend like it actually goes through there, there's a whole other there's an imaginary axis coming off of each of the x-axis and the y-axis. There's an imaginary axis. So if you have, so this is our situation, yes? This is 4 here, yes? If I looked at the complex axis that comes up here, this does this. So if I go far enough, it actually intersects at 2i and negative 2i. Trippy. So imaginary numbers, stupid ass name. When we first came up with negative numbers, they called them imaginary because they were like, what the hell? If you have 2 apples and I take 3, you have a negative apple. What the hell's that all about, dude? Don't let me near your apple black hole, okay? But it's just, if they exist, they're orthogonal to each axis. There's a whole other complex axis, which is why it's actually 4 dimensions. If you're trying to graph something truly, there are 4 dimensions here. We just do a slice, because I don't want to look at that shit. Yes? Is that okay so far?
Yeah.
Okay. So this half rotation is the square root of negative 1. It exists. It's not imaginary. It totally exists. You can't do all of electromagnetism without the idea of complex numbers. They call them J because they're weird. We call them I because we're normal. Okay. Sorry. A lot of you guys are future engineers. You're all weird. Okay. It's okay because I'm weird, so it's all right. So if I apply another one, which means square root of negative 1 times square root of negative 1, I sure enough get negative 1. So this is the first thing we've ever seen, that if I multiply by itself, you get negative. Okay. Is everybody with me now? This whole idea is going to come into play later. In fact, when you learn this kind of stuff here, this is all about rotation. If I rotate by 180 degrees, aren't I at negative 1? And all this says is negative 1 plus 1 is 0. Whoop-de-doo. So e to the I pi over 2 would be I, because that's a 90-degree rotation. All right, Jeff. Good Lord, go away. Okay. So coming back to this. Sorry. Just real quick. If I just pick the 2i, what does my matrix look like? It looks horrific, yes? Poor little guy. Negative 2i, 2, negative 2, 2i, negative 2i. Yeah, you got it, Jeff. So do you see how this is, well, do you guys see this? If I multiply the bottom one by negative I, let's say. Bless you. What do I get? Negative 2 times negative I is 2i, yes? What's I times I? Negative 1. Cancels with that, but then there's still a negative here, yes? And then wouldn't that row reduce to be this? And then I could find the eigenvectors, yes? Okay. I'm not going to make you mess with those too much, but they exist. So then, I mean, your answers are just going to be complex. It's just too bad. So then I get negative 2i x1 plus 2x2 equals 0. Therefore, x1 is negative 2. No, Jeff, the 2's canceled. Negative 1 over I, which you can figure out what that is, by multiplying top and bottom by I, and you end up with I. So then you get x1 is I, x2, so you get I and 1. Okay. Where the crap did he do that? Okay, that's enough. Same exact work. You just have to remember I times I is negative 1, that kind of stuff. But the math is basically the same. I just get a letter suddenly showing up in my vector. Okay. Is that okay? We're not going to do a ton with that because we're not going to suddenly become like complex variable central. Okay. Blah, blah, blah. What's really important here? This is important. If A is invertible, with eigenvalue lambda, then A inverse has eigenvalue, who knows? What would be your guess? Yeah, that would be my guess too. So let's see. Let's assume A is invertible, and I set up this equation, yes? That's the underpinning equation for the entire idea of Eigen-stuff. If A is invertible, can't I just apply it to both sides then? So then I get x is A inverse lambda x, yes? Then can't I take the lambda, it's just a number, correct? So can't I take it out front? And then can't I divide by lambda? And doesn't that say whatever this eigenvalue is, the inverse has 1 over it? Yes? Is that okay? No? Do you see every step? Do you see how every step is pretty simple? If A is invertible, I just apply the inverse to both sides. Lambda's a number, so can't it just come out front? Yes?
Would you just have taken the determinant of y of lambda a inverse x?
Do what now?
Take the determinant of the right side. The determinant of a inverse is just 1 over 8.
Oh, I see what you're saying. Okay, you could work that into this. Sure. That would change kind of like how I do the proof, but that would also, I think that would get you where you want to be. Okay. You're just using the relationship between the determinant of the A and its inverse. Yeah, I like it. Blah, 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 blah. So here's where we're finally headed. Given a matrix A, I could find eigenvalues and eigenvectors. If I collect, so for example, let's go back in time for a second to a nicer thing. So we did this problem earlier, yes? Okay, so for A equal to 1, 4, 4, 1, we got eigenvectors of 1, 1, and 1, negative 1. Guess what those two vectors span? They span the eigenspace. Somebody out there must have known eventually this is going to become a space. So we're collecting these eigenvectors given a certain matrix. So if I just put them together, they form a basis for eigenspace. If my matrix has enough eigenvalues so that its eigenvectors span the space it's in, let me say that again. If my matrix has enough eigenvectors to span the space that it's in, that eigenbasis is the best basis. It is the best basis for everything happening in that space. So one key question in this class that's happened over and over and over is, what is the best basis? So we know that the best bases are orthonormal. That would be great. But when you force them to be orthonormal, you very often get these funky ass looking things. You're like, that doesn't look very good. But there could be a reason that I want to force it to be like that, yes? But what generally is kind of like the best basis is actually, if you can get it, the eigenbasis, which would be just the collection of all your eigenvectors. What was it that led to, which way do I want to go? I think I want to go blah, 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 blah. what leads to these being, this specific problem was nice because what's true about these two vectors? I don't know if you guys remember, this is a real symmetric matrix. What's true about the two vectors I get from that situation? They're orthogonal. Yes? Which is awesome. That's beautiful. Okay. That's just a quick side note. Let me see. What did I leave out? Not too much. I feel okay about that. Just a very quick side note here. If lambda is an eigenvalue of A, lambda to the n is an eigenvalue of A to the n. In a sense, oh, I'm sorry. As I was writing, you're like, we hear you. In a way that's kind of silly, because what's ax? If that's an eigenvector, it would be lambda x, correct? And then what is a times ax? That would be a times lambda x, which is lambda ax, which is lambda squared x. So then a squared is lambda squared x. And you just kind of keep doing that until you go a little, oops. Beep, beep. You just keep doing that until you go a little insane. And you realize a to the n. This matrix has this eigenvalue, yes? So a to the 99th would have lambda to the 99th as its eigenvalue. Okay. All right. So I think the last thing I want to talk about today, don't get too excited. All right. So let's see. How do I introduce this? This gets trippy. All right, let's do this. This is 6.2 officially. I'm going to talk about something about, it's called similar matrices. They are effectively matrices that cause the same transformation to happen when you apply it, but along different coordinate axes. So they cause the same transformation to happen, but along different axes. That's not the practical definition of similar, though. It's kind of like, how do I see that? I don't know. But that's what they do. Now, how do I determine if something is similar? Well, let's build something that's similar to something else first. So here's how I build something that's similar. So if I have A as a square matrix, if there exists, by the way, this is the symbol for there exists. Maybe I shouldn't all of a sudden start using that. There exists a matrix C such that B equals C inverse AC, then A and B are similar.
What's the word after matrix?
Who knows? Which matrix? This one.
Yeah.
Such that. Yeah. So all right. This is very trippy. This is a very, very basic definition, and then we're going to make it a little more focused on our immediate. So somehow I'm going to tie this into eigenvalues. But this idea just exists. So we could actually develop. So what if A is 1, 2, 0, 3, and let's say C is 1, 0, 1, 1. Can you guys tell me very quickly what C inverse would be?
1, 0, -1. Oh.
Yeah, 1, 0, -1, 1. Kick ass. So real quick, we're gonna build B. B would be C inverse times A times C. So just to kind of cut to the chase, if you do all that, you'll get 3, 2, 0, 1. Now, in this case, they happen to have, what's really interesting is, it's kind of like I took this and I went, eek. Yes? That's not always going to happen. So these two are similar. In fact, this is kind of nice. This is perfect. I didn't realize this until now. This does the same thing this does, but along different axes. In fact, perfectly, whatever this does along the x-axis, this does along the y-axis. This is like a perfect rotation. That's crazy. But it doesn't have to, so I just happened to pick one that kind of ended up that way. Okay. So similar matrices are two matrices that are somehow connected to each other through this third matrix C. Can you write an expression for what A is? I wrote what B is in terms of A. What's A in terms of B? Here's B in terms of A. What's A in terms of B?
C inverse.
Yes, because you have to multiply both sides on this side by C and on this side by C inverse. So you get C, B, C inverse. Cool. Just a little side note. One little thing to notice, and this is kind of almost too nice. I have to see if I have another example that's a little bit more disgusting. Oh, no, shoot. All right. But here's a couple of things. If A and B are similar, the determinant of A equals the determinant of B. And really quick, this is actually really easy to prove. So let's look at the determinant of B. And if I just use the, if they are similar, that means I can rewrite B in terms of A like this. Is that cool? Yeah, like that. Whatever that is. CAC. And how do I deal with this?
You do determinant of C inverse times determinant of A times determinant of C.
Now, aren't these just numbers, each of these?
Yeah.
Okay, so can't I just change the order in which they are written? Because they're just numbers, so I can use commutativity if you want to be all formal. Can't I put these back together then?
Mm-hmm.
And what would this be? 1, yeah, so then determinant of B equals determinant of A. Neato, neat, Jeff. So this is a little theorem here. And then also, if A and B are similar, I would hope, if we're going to call them similar, it's got some more stuff that they kind of share. They have the same eigenvalues. But they do not, they definitely don't have to have the same eigenvectors, which makes sense because one matrix lives according to a different orientation of axes. Yes? They have the same eigenvalues, but not necessarily the same eigenvectors. Okay. Up. Yeah, let's see what's important here. Yeah, that would be important, wouldn't it? Oh God, how am I gonna do all this? All right, so let me show you this. Yeah, let's do this. Okay. I think this might be the last thing for today. Let's see, which is unfortunate. How close did I get? Only 6 pages away. Damn you, Jeff. Okay. So let's look at this matrix here. Just because. Nothing really special about that poor little dude, right? It's invertible because the determinant's not 0. It's not symmetric. So there's nothing, special about this poor little dude, poor little guy. If I set up what I need for the eigenvalues, I'm just kind of going through this really quickly because you guys can all do the multiplication and so forth. You get to there. If I set this equal to 0, I'll end up with lambda is 2 and -1. So here's where things get interesting. And I'm just going to kind of show you this, and next I'm going to have to try to prove this. If I look at lambda equals 2, I'm really going to cut to the chase here. Go through all the stuff, set up the freaking A minus lambda matrix. I would end up with, I hope I did this right, past Jeff, 1, 1 as my eigenvector. You guys with me? Lambda equals, what was the other one? It's right there, Jeff. -1. That leads to an eigenvector of 5, 2. So, create matrix C by just throwing my eigenvectors in as columns. Create matrix D by, matrix D is going to be like lambda I, basically, but it's going to use both lambdas. So I'm trying to give you a way to kind of remember this, but if I just throw both lambdas, they have to go with the correct eigen. So this is first, so that the 2 better be first, because that's where that came from. This is second, so the -1 better be second, because those 2 go together. Does that make sense? And can somebody, what would C inverse be here? Yeah, -1/3.
Times 2, -5, -1, 5, or 1.
Okay, is that cool? Now, I'm going to set up something that should look very familiar. C, and familiar in form. C, D, C inverse. That's kind of like the similar thing we were talking about earlier, yes? I know this is coming out of nowhere, and I'm sorry. I'm trying to figure out what I can throw in here at the end. Well, we can do this. This is just straight up stuff, and then let's see what this becomes. Good Lord, Jeff, this better become something. This is the inverse of the CDC, which is basically what RFK wants, but that's okay. We'll be all right. We're going to survive. Sorry if you have a certain leaning. You're just being silly. So C, drank too much raw milk. D, and then are you guys cool with this? I'm going to put the -1/3 out and just leave the heart of the inverse over here. Is that cool?
Yeah.
Something you can totally do. We did that with our projection matrix and our whatever. Yes, our Q matrix and so forth. You can just leave the multiplier out front, so you don't have to worry about it to the end. If I do this, just continuing today's, what do you call it, theme of hiding all the work, you eventually get to here, and of course that just becomes -3, 5, 2, 4, which was our original. So this factorization does not seem good. Does anyone believe that that's good?
No.
I don't blame you. I love some of you guys are like, I don't want to say no, but it's not good, Jeff. What are you doing, man? Here's the beautiful thing. Here's the absolutely beautiful thing. Has everybody got what they want from that? Probably not. I'm sorry. Too bad. If I have this crazy ass dude, and I want to figure out what a to the 100th power is, do you want to do that by hand?
No.
No. Okay. So what I can do instead, since I have factored this, if I want to know a to the 100th, this would be just this. And why is that nice? Because D, why do we use the letter D? Because that is diagonal. That one will always be diagonal. Any power, therefore, is stupid easy. I just put powers on the diagonals. If you don't believe me, you can try it. You can see it's very nice. This is crazy. So if I factor this and I have a computer calculate this, this is going to be a lot easier than actually doing this thing times itself 100 times. You're going to save a ton of freaking workload, calculation time. And what I want to do with my -2 minutes left is show you, where did I put the proof of this? Damn you, Jeff. You have hidden it somewhere. Damn you, Jeff. Oh, yeah, of course. So watch this. If I would do a squared, that would be this, yes? Yes?
Mm-hmm.
And then I could just write this. Is that cool? Yeah, there we go. Then you get all this nifty collapsing happening, yes?
Yeah.
These become 1. D times D is, and then if you want to do 100th power, you just do that 100 times. Yeah? So that proof kicks ass. Such an easy little. I'm really sorry. That was fast. So over this weekend, I'm gonna work on the plan for, next week. On Monday, wait a minute.
Monday we would be to practice.
Monday's our last day to do new stuff.
Yeah.
I'm gonna give you the practice final, I believe, on Monday.
And then
What is our review day?
The 21st.
Wednesday.
Yeah.
Is that next Wednesday?
Yeah.
Yes, it's a week from today.
That's the 26th.
So I'll have the practice final on Monday. Review for the final is a week from today. We're almost definitely not gonna be able to do every section left.
Memorial Day.
So if you wanna get ahead, go for it.
Okay. And then Wednesday is the final, and then next Monday.
The final's over 2 days.
And then our review day for F3 would be the 28th.
Think so?
And then our last lecture day would be
I think I put our test on that Monday, right? The second? Yeah,
yeah.
yeah.